Okay, and we're back with part 2 of game AI architectures, the anticipated. Today we're going to talk about kind of building some of the actual architectures behind building out, reactive behavior frameworks for AI. Because often you don't have, you're not just like writing code to just sort of transform things into other things. You're actually building out a underlying system that is then going to manipulate an object or an entity or something in your game. And so, we really want to frame this in the context of behavior and how an agent is going to react to state, make a decision, and then do a thing, and that's going to give you a new state, and yada, 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 right? So, in the 80s, Rodney Brooks devised this control method for robots through layering sort of simple reactive behaviors. And so this was called the subsumption architecture. And this is a forerunner for Craig Reynolds' steering behavior. So anybody who's taken 202, right, you're probably familiar with this. We even talked about this earlier in the course. And I think, the paper is up on my courses as well. And so this thing called the Stanford Research Institute Problem Solver was something that kind of came out of SRI in 1971. And this was sort of an early simplistic sort of planner, automated planner given sort of goals and states and things like that. So let's kind of talk a little bit about this. And in strips, I'm not super familiar with it. It's something that has been around, was around very early on, and so it doesn't get used that much anymore. But essentially has a set of, an initial state and actions and objectives. And as you layer these actions on with objectives, you sort of transform the state, and it's almost like one layer above functional programming in a way. It's sort of like each function has a very agreed upon contract of expected, things that it's going to change, things that are going to stay the same, and how things change based on running this function. And you can kind of layer them in almost like functional blocks given objectives. So it's almost like I'm hungry, and hungry means eating, so go eat something. So it's like not specific to what, it's just to eat something. And by eat, now I'm in the eating state and things like that. So here's a good example of this blocks world. So this is like a simple domain for testing and planning for these systems, right? We have, in this case, 4 actions, right? So one action is to unstack A and B. So it pick up a clear block A from block B, right? We can stack A and B, place block A using the arm onto a clear block B, and pick up A, lift clear block A with the empty arm, or put down A, place the held block A onto a free space on the table, right? So in this case, A and B could be any block A and B, but they're a particular block A and B. It's just like a function. Like we're inputting to it a thing, right? And it requires some predicates, right? For unstack, on A and B has to be true. So block A is on block B. If you try to unstack A from B and it's not there, then, see you later. Same thing with stack on table. Block A is on the table. Clear A, so A has nothing on it. Holding A, the arm is holding A, or arm is empty, the arm holds nothing. So these are sort of these predicates that need to be true or false depending on the function that you're calling. And so these things, so if you can't unstack A from B if A is not there. You can't pick up A if A is not on the table. So for example, if it's stacked on B, for example, right? So I just went through this, right? So you have a lot of these sort of predicates and post conditions, right? By unstacking A and B, right now A will be on the table, and B will not have anything on top of it. To stack A, you need to have A on the table, so on. I recommend you go through this on your own and kind of work through all of them individually. So using strips and block worlds quite straightforward, right? You have an initial state. You can then, check on A, clear A, on table B, clear B, on table C, clear C, and arm empty, right? And our goal state is going to be clear C on table A, on arm empty. Right, and so this it requires like, well, based on these initial states, right? What plans would get us to those states, right? And we can kind of just figure this out using a finite state machine of some kind. So that's really it. I mean, that's kind of the beauty of this approach, is that you have these functions that transform the world, and this looks a lot like that production system that we talked about in the last lecture. I'm not going to work out through these, and I recommend you try it, right? So if your initial state is A is on the table, and we want to, you know, get to on table A, well, we're already there, right? But say we have, you know, on table A, and then we want to have, you know, on B on A, then we have to, right, A predicate that B is on the table, and then place B on A, right? So that's just one example. Cool. So this sort of, we talk about this, right? But what's actually going on? And again, like, it's just this sort of underneath the covers, it's a finite state machine, right? So you're you have a set of states, right? The state of the in this case, the state is the state of the table and the arm, right? And by applying any one of these functions, you are now changing the state, and you can codify this in some kind of finite state machine, because there's only so many states. And you might not necessarily treat it like a finite state machine, right? You might just have it like as states, and the states are, there's a bunch of states, right? Like, you know, you might not code it like this tree, like we talked about, or a graph, but rather as a set of variables that you're updating and manipulating. But regardless, that is still a state machine. You're just not treating it that way, and it's a lot easier to design, right? So like, imagine a tree that has apples, right? And we're picking the apples, right? I can only pick an apple when there's an apple present. If there's no apple present and I pick an apple, it's error, and it's not going to let me do that, right? But by picking an apple, the number of apples has gone down by 1, and then maybe some other process is randomly spawning apples at some kind of cadence. So again, it's just applying functions to an underlying set of state variables. And what's cool about this, by the way, is that all of a sudden, by not having to create an actual state machine, you can deal with continuous variables, right? It's sort of like, I'm at position 7.3, and I want to, you know, move forward, and moving forward takes me to 7.7. It's not. This is something very intuitive, right? Like, I'm applying thrust, and that's going to affect my position. And if I'm trying to arrive at a certain place, I have these different sort of behaviors, like what we talked about with Reynolds, right? With steering behaviors, that helps me accomplish those goals. So Fear, the video game Fear. Some of you use this as your project for the assignment. You know, it uses a modified strips system, and as much as it may be an old system, it works, right? It's predictable. It works quite well. Relatively straightforward to implement, and many of you have likely implemented this without even realizing it. Just something. It's kind of an intuitive way to design these things. So yeah, Fear uses this modified strips planner to make decisions, right? An action in this case is described by the precondition and the effects of the action, right? So for example, this fun example with dominoes, terrific, right? My state is like, what's my phone number, my recipe, am I hungry? And the goal is to not be hungry, right? And the other things, the states don't matter, right? And so I start off with my phone, I call, and I'm hungry. Dominoes comes as a result of my action, and then my phone is still the same, and I'm no longer hungry, and the recipe is irrelevant. Or if I'm baking a pie, same idea. So it's like a lot of ways to kind of describe the same thing. I apply a function, things happen, and that changes my underlying state. So the differences from strips is what's called, sorry, I'm not explaining this well, but there's another thing called what's called GOAP, or goal-oriented action planning. And what this does is, so in strips, you don't really think about, you know, it's kind of this exhaustive search of actions and hoping to get to where you're trying to go. And for the most part, it's not even that sophisticated, right? Like I said about steering behaviors, you're not doing some kind of planning of like A to B to B to C to C to D very often. it's usually kind of one hop, or there's some kind of value you're trying to manipulate directly. And so if you want to do something a little bit more sophisticated, where you might have multiple actions to arrive at a particular goal, GOPE is sort of the strategy there, what's called goal-oriented action planning. Goal-oriented action planning. So what you do is now every action that you have has a particular cost, and then we just use A star to search that, right? And the heuristic that we're using to guide A star is essentially the goal, right? So you can kind of imagine a scenario such as what I talked about before, where you're flying a spaceship, and you want to fly to a particular point, but going at certain speeds requires more fuel, and that's a cost, and that's your heuristic. And so you can kind of figure out, maybe if I bank off of Saturn with, like, you know, bullwhip with the what's it called, the slingshot and whatever, and you can kind of come up with a more optimal way to accomplish your goal, because otherwise you wouldn't have enough gas in the tank or something like that. So, you know, this is sort of the idea behind GOPE, and you can have procedural preconditions, you can have procedural effects, right? So you don't have to have it contained into this just your state. I'm not really sure what this one means about eliminated add and delete lists for effects. I think the intention here is that, and this is true, right? Whereas in A star traditional, like for pathfinding, your world is sort of contained within this thing, whereas here, right, at every iteration of this algorithm, the state that you're operating on may be changing quite substantially, right? So that's kind of something to consider, right? So in this case, the preconditions and effects, right? You have an action, you have the state preconditions, you have the effects on that world, and then you want to check those conditions, and you activate that function, that action, right? So you activate the action, and the preconditions are not valid, then it won't actually run. You can't, for example, fire the thrusters when your gas is out, and you can also not, you know, move forward when there's some kind of effect being applied to you, like, for example, a gravitational force or something. So there are things that exceed the system that you're in sometimes, and those things may be changing. So, for example, in the game of Fear, you know, different kind of AIs had different sets of actions that it could take. For example, the rat, which has the most small amount, is like animate, idle, go to a particular point, or use some smart object node, for example. Whereas the soldier has many more, right? Reload and attack, and the assassin has, you know, attack from ambush, right? And attack from ambush, for example, is a really good example, because you can't attack from ambush unless you're in an ambush location, right? So you have to, you know, get to a position maybe that involves the survey area action, or something else like that. I'm not too familiar with this, right? But you can see traversing all over the place, right? And these are things to get the agent to the place that it needs to be. So what's cool about GOPE is that it decouples actions from goals, right? It allows this sort of emergent behavior, because many simple behaviors can be chained together, and to accomplish the same set of goals, or even disparate goals. And this gives you an ability to problem solve in kind of dynamic ways, meaning in some cases it's not going to behave the same way to arrive at the same goal, depending on a changing set of state variables in your environment. So this is kind of cool. So NOLF2, which I'm not familiar with in the game, versus Fear, right? In NOLF2, branches needed to be added for any variation among different NPCs within a black box finite state machines, right? So you can see on the right, Fear uses this FSM within this one kind of unified working memory around all these different things, whereas NOLF2, again, I'm not familiar with that game, I apologize, but each one of these sort of behaviors had its own internal finite state machine. You can kind of imagine how these things interact as a result, right? And if you've done sort of flocking behaviors like steering and so on, you might kind of appreciate this, because multiple agents may be not just interacting with their own goals, but with those of other agents, right? And in a way, this is sort of the same idea, but within one agent, right? So like one agent has multiple things, multiple finite state machines that it's operating on that are all working off of the same, like reacting to the same set of underlying variables, but meaning that you get very dynamic and emergent behavior in these individual finite state machines because the state machine is encapsulated to this thing and can't address the underlying component except for indirect methods. Whereas in fear, for example, in this sort of strips approach, everything's shared, and so all these sort of behaviors are applied to the same set of variables. And so while you still get some good behavior out of this, it's not as like flexible or dynamic. Sometimes that's bad, right? Sometimes you want behavior that's kind of predictable and doesn't do things that surprises you, right? But sometimes you want AI that's a little bit more interesting and behaves in a more fun, interesting way. So layering behaviors, right? Like, what if you need to turn the light on every time you enter a room? You kind of understand the benefit of having layered behaviors because I want to enter the room, but I also want to turn on the light, right? And these are two kind of independent actions, right? I shouldn't enter the room, stop, then go turn on the light, stop, and then go do whatever I'm doing. I'm going to walk by the light switch and turn it on while doing other things. You can kind of layer these behaviors on top of each other. Right? So, an example of this, like what happens if the player blocks the door after running inside? What do? How does the AI respond? It has to respond to this different state. It's not going to just walk into you and just keep bumping into you until you move out of the way. So here's an exercise for you to try in your own time. You can pause and try it out. Right? Imagine using goal-oriented action planning for first-person, enemy AI. Right, you can have all these different, goals and a bunch of different actions, right? And what are some of these simple behaviors that you would chain together to achieve these goals? And so, like, try to work out sort of a simple plan to attack and kill an enemy in this case, right? You might want to first, go to a particular location to get into an ambush state, and then whatever. I'm not going to do this for you. Hit the pause. Give it a shot. Where else is the AI, right? So what about squads, right? So we've talked about individual AI. Sometimes you want to manage the squad or a collection or a population of AIs by a higher order or a meta AI that kind of does things or squad behaviors, right? If you ever played a game like StarCraft or what have you, you kind of have dealt with this where you select a number of units and they all have to go, and all of a sudden one unit bumps into a rock but the other ones haven't, and it still has to kind of connect to the unit, to the squad, but get around that thing, and maybe the squad has to slow down to wait for it to catch up and things like that. So it's usually a centralized AI that does these things and not part of the individual AI. Right. So, like, for example, there's a StarCraft example, but like if we get to cover, so imagine you have a squad and all the members have to get to cover while one member of the squad lays, some suppression fire, or two AIs are firing at the player and the player takes out cover for one of them and things like that. So it's a lot of fun emergent properties here and a lot of way to add depth into the AI by having these sort of hierarchical layers, which, by the way, is exactly what GOP is, right? But at the level of the AI. So you can kind of see that the AI hierarchy kind of exceeds outside of an individual unit, but also can be kind of in a meta thing. And even you can think about globally, right? Like the environment as an AI, you can kind of codify as well. You can imagine kind of a similar example, but for complex behavior, right? But, the only cover that the AI can find is around the player and behind them. And in this case it can be perceived that the AI is flanking, but really it's just seeking cover, and then all of a sudden finds itself in an interesting, unique place, right? Same thing to advance to cover. AIs can get close to the player, but it happens right on obstacles on both sides, and it seems like an attack of some kind. So like you can see how these emergent properties happen out of like, oops, like sorry, our AI is trying to do something just naturally out of this goal planning framework, but all of a sudden the player sees a much more interesting behavior arise out of that. It's cool. So, you know, what squad behavior? So here's a question for you. Pause the video if you'd like. What are some of the squad behaviors you would want or need for an enemy first-person shooter AI? Bueller? Cool. So some code examples are available at gope.html in this wacky URL, so feel free to check this out. But you can kind of, there's a lot of great resources on this. Yeah, so final system to kind of explore is what are called blackboard systems, right? And this is sort of a way to kind of consider a shared state across many different AIs. The example is you have a blackboard, that's the state, and everybody has access to it. You can read and write to it. If you've taken any kind of class around concurrency, you can kind of imagine all of the different problems and bottlenecks of this, but imagine a perfect system where the underlying state variables are manipulatable by anybody at any time, and the dynamics therein of pushing this. Imagine, like, for example, a game of tug of war, right? Because both players, and this is an adversarial case of Minimax, and it's a Minimax game, right? But both players are actually addressing the same underlying state through some kind of dynamics. And that's sort of a version of the blackboard system. It's a shared thing. Usually it's not, you know, this adversarial thing, but that's a good example of it, right? So blackboard system contains agents that solve problems and the shared memory, which is the blackboard. Again, we're not talking about the concurrency aspect of this, but that's a really big, important thing, right? And then you have an arbiter that determines, you know, what should happen, what actions can happen next in terms of the agents that want to update things. And often the arbiter is very simple, such as just the concurrency method to update the state, or it can be very complex in the case of, you know, say, like a game of tennis. Well, a game of tennis, we might not want to do this because, but like maybe a game of hockey, right? Everybody's manipulating the same puck, and some things are not allowed. Some actions are not allowed, right? So here's an exercise: is think about what's a blackboard system for a first-person shooter AI, right? What agents are changing the blackboard and performing actions, and what does the arbiter do in this case, right? Like, in fact, what does the data even look like for the blackboard? So this is a good place to drop off, because you can kind of think about, again, think about this in the context of strips and Gope, and you can kind of imagine ways to do this. And actually the hockey example is a really good one. Like, what are the shared variables that a first-person AI is manipulating that would apply to the player, but also other AIs in the system? And with that, we're going to finish the lecture, and I'll see you next time.